Okay, so far we have looked at a situation where we have systems that are statically determinate, systems that are statically indeterminate, and now we'll look at one that is statically unstable. Right, so here again, we're still going to count up the unknown number of forces, the reaction components here in this case with only two rollers. We have one independent reaction component each of those, so we have a total of two. And then the number of members is back to that original configuration, so that's 13 if you count them all up. And of course then U equaling the number of total unknown forces. We have R plus M, and that's equal to 15. We have still 8 joints, so total number of static equations of equilibrium is 16. And so with that then, we don't have enough force components to be able to satisfy all the equations of equilibrium. Hence, this is a statically unstable situation. Right, now compare that down to what we have below, and it's similar, but not quite. It's actually quite a bit different, similar to all the things we've been looking at, but take a look here. In terms of our equations, we're back to, again, n equaling 2j equaling 16. Right, now, if you look at our unknowns that we've got here, unknown forces, our R, notice we have a pin there, so we're back to 2 there plus the roller, which is now on a vertical plane. So that's what's different here. But mathematically, that equals 3. M is equal to 13. Our total number of unknowns is 16. 16 equals 16. It should be statically determinate. But the problem is that when we look at the global free body diagram, the reactions are arranged differently. And so now with that roller being on that vertical plane, then that means that reaction is horizontal. And so the reactions form a concurrent force system. And that's bad, because look what happens if we were to apply a load. Let's say it's at this bottom chord joint, that's P, it's at some distance away from the left support, let's call that A, right? And write a equilibrium equation, and look what happens here. Well, some moments about point A, let's take clockwise positive, and we get P times X, but the problem is that's the only thing in there that has a non-zero moment arm, right? The Y component goes, the reaction goes right through A, AX goes through A, and then this was called joint E, so EX goes also through A. It has no moment arm. Of course, if it's static equilibrium, that has to be set equal to 0, and the problem here is that X is not equal to 0, so therefore P must be equal to 0 or we can't resist any load. Well, but wait a minute. That's the whole point of the structure, is to be able to resist a load. So that's why we end up with it is mathematically unstable and it is physically unstable. Right, so it's not enough to have these numbers be equal to each other or the number of unknowns exceeding what we have to have. They have to be arranged properly, and when they're not, then we have what's called a geometrically unstable situation.